Okay, so welcome back. So today, the goal for today is to finish this quine discussion. So if you remember, we started writing a quine in Python, kind of putting into action what we learned about how do quine works. So if there is one thing you should remember from last course is that to make a self-reproducing program, the main trick is to have one part which is the data, one part which is the code, and then the code uses the data to print the data, and then it uses the data again to print the code. That's the one thing you should remember if you have to remember anything. So today we're going to finish writing this quine in Python. After that, I'm going to show kind of the more mathematical proof, like rigorous proof of the existence of the quines. And then after that, we make a pause on the theoretical stuff. I'm going to start looking at actual implementations of cellular automata. So it will be much lighter if you were kind of scared from the previous courses. And so we're going to look at the one-dimensional cellular automata. And I'm going to try also to show you kind of some basic skeleton program which you can very easily use to implement a cellular automaton. All you need is to write the rules of evolution, and then you can see it evolve very easily. Okay, so let's get back into the code. So let me remind you what we have done until now. So we first start with kind of a setup. It's not really the quine. We kind of define the functions that we'll need later. So as I said, we need a way to be able to write the special characters such that they don't act as special characters. So this is what we define here. So we have the quote variable, the enter variable, the slash variable. And then we define a function replace. And all it does is just, it takes a string and it replaces some aliases that we have here with the actual characters. So this one will be replaced by a quote. This one will be replaced by an enter or return. This one will be replaced by an anti-slash. And additionally to that, we have two free variables, which have some predefined aliases, which can be replaced by any other string that we would like, okay? So free1 can be a string, and all occurrences of the alias f1 will be replaced by this string. Okay, so this function replace is very basic. In Python, if you know Python, it's basically hard-coded into print. You can use print to do what replace does, but we don't want to use Python-specific stuff. We want to do it as general as possible, so we define this replace function, okay? So then once we have kind of our setup, we start defining the data. Okay, we said, what is the data? Well, the data is simply the source code of our code. So we start, we're going to do it in several variables. We could do it in one variable, but it's not as clear. So we have data one will be just the first 3 lines of code. So it's these 3 lines. And of course, here we have a bunch of special characters. So here we replace all the special characters by their aliases. Okay, so these are all these things. So this data contains this part. And then we have a data 2, which contains this full function here. And here we had to do some shenanigans to be able to actually print these special characters, which are usually aliases. We need to do some kind of trick to not replace those special aliases. But okay, we succeeded. And so now if we print replace data 1 and then replace data 2 with those shenanigans, what we should get is the first part of our code. So let's write here. So I'm just going to send this into another file so it's easier to see. Okay, then if I open the quine copy, okay, we see that we have successfully produced the first part of the code, right? There's this thing and the replace function. So up to here, maybe I'm going to zoom out a little bit. Is this still readable? I guess so, right? Yeah. So we have printed this first part here, and now we start to have the issues. So far, we didn't have any special issue, and now we need to start to print the actual data. Okay. So let's start to do that. So again, the data is part of the code, so I will put it inside another data variable. So the naive way to do this, which is the wrong way, as we'll see, is to say data 3. What should be data 3? Let's say data 3 will contain this block here. So data 3 should be, well, data 1 equal, and then I should put this thing inside. very naively. Okay. But if I do this, okay, I have to replace some aliases. So we first have a problem that we have some aliases that should not be replaced and some others that should be replaced. That's the first problem. And the second problem is that if we do things like that, we're never going to end. Right? I'm going to use data3 to print data1 and data2, and then data4 to print data3, and then data5 to print data4, and I'm doomed. So now we remember the key feature. We need to use the data to print the data. So here, instead of just copy pasting this, I'm just going to say, okay, I'll just put an alias f1, right? And when I will print it, I will say, just replace this f1 by the value of this variable. Okay, so let's see it. Let's put also data2. So data1, we also need the quotes, right? The quotes here around the value. Then we have 2 returns to get to data2. And then we have data2, so GitHub Copilot gets it wrong, actually. So GitHub Copilot should be F2, right? The definition F2. And then we can put another enter. Okay, so data3, what does data3 contain? So it contains data1 equal something that we might replace by anything. Then data2 equals something that we might replace by anything. So if I do print replace data3, and I say the f1, I would like to replace by the value of data1, right? And the f2, I would like to replace by the value of data2. So what will happen here? So, of course, the special characters will be replaced by your function. But in addition to that, we'll take this f1 and plug this thing into it. Okay. So this is the crucial part. You see, we used data1 to print the code. So we used it to print this. But now, here, we reuse it again to print this line here. So we use the data twice, and that's the trick. Okay, let's verify that I'm not bullshitting you. So if I run this file, we go into quine copy, and as you can see, we also copied data1 and data2, right? Okay, you might say, okay, that's great, but you're not much closer to the goal, because now we're until here, we still have to print all this stuff here. But now we're kind of fine, right? In this data3, I could also add this stuff here. So let's do it. So after data2, I should use 2 returns. And then this is just some text. Then a return. Then this is just some text. We need to replace the quotes by the alias. Okay. All right. So this should be, it's missing a parenthesis. Right, so now if I run it again, whoops. We have, here. Yeah. If I run this again, now what? Now data3 contains this line, and those 2 lines. Okay, so we made progress. So now we kind of caught up, right? We wrote almost, and we still have this print, but we printed up until here, and we defined data3. Data3 helped us print data1, data2, and a whole bunch of stuff. And so now with data4, we're going to be able to finally close the loop. So what will data4 be? So data4, we still have printed until here, so it should contain this data3. And again, we do the trick. So we use data3 equal. We're not going to copy paste this part here. We're going to use data3 to print data3. So here I just put f1. Okay. And now that's the magic, right? Data4 can be used to print data3, but it can be used also to print itself, right? Because here I can just put 2 enters, and then data4 is equal to f2, right? And that's the magic, right? Because in data4, if I did it the naive way, I could never copy paste data4 into data4, because that would change data4, and then you'd have to copy paste it again, and so on and so on. But here I say I kind of defer the printing of data4 to later. I just say data4 will be equal to something of my choosing. And then all I have left to do is print data4, right? Data4. we want to replace free1 by data3, which is this f1, and free2 we want to replace with data4 itself. And then this will work. So as you can see here, we are printing data4, but using it twice. Once to print like this data3 and data4, and once to plug this thing in here. Okay, that's kind of the mindfuck. But now we are caught up because data4 has printed up until now, up until here. Okay, we still have the two further prints statement here, the print1 and the print2, but these are just plain text. There is nothing special happening here. So I can just put two returns here, put this sentence, then one return here, and put this sentence here. And now, as you can see, data4 contains the data up until there. Okay, so let's try to run it again. Let me see. There is no. Let's see it. Okay, so it looks pretty good. We have data3, we have data4, we have the two prints at the end. Okay, now we have a nice feature in VS Code is that we can compare two files, because I'm sure I probably forgot some spaces somewhere. Okay, so here we have the comparisons of the two files. They are pretty much the same. Okay, we have some extra spaces, some missing spaces, but okay, that's fine. We just have to add some enter somewhere. It's not very important. And yeah, and so this is a quine, right? So if now I run the quine and I put its output into quine copy, and now let me run quine copy and put its an output in quine copy copy. Okay, there is a problem. Some special character. Start non-UTF-8 code starting with XFF.
Line 1.
Very strange.
As the print of line 1. I mean,
yeah, but I don't see why. Why is it making a special character? No encoding declared.
But if you do Python quine copy and you copy paste the result.
Yeah, probably. Yeah, let's copy paste that into into a new one.
No, copy. That's not what I meant.
What did you mean?
Instead of doing Python going to the file, just print Python quine, run Python quine API.
This one?
Yeah, and copy paste.
This, yeah. Okay, and then this is the copy. And now can I run the quine copy? Okay, there is a strange thing with Python. Okay, it's not a problem with the quine. I mean, the quine clearly works. It's the same text. I must have done something strange in the replace, which is not happy about the encoding. Okay, I will have to check. I will not debug it now. I'll try to debug it during the pause. But the point is that we do have a quine, right? It outputs its own code. And as you see, this is kind of typical of the quine, right? You start writing the quine and you give up some progress, right? Because you write a bunch of code. Now you wrote a lot of code that you're going to have to print a lot of code. And so you're starting defining the data variables that hold this super long code. But then it means that you need to print also these data variables. So you need to define more data variables. But as you go on, these data variables, they're kind of able to print more code than they generate. And at some point you catch up. So data4 prints data3, so this part here, but also contains itself and also what's after itself. And then you're good and it's a quine. Okay, so just in Python, you will see if you look it up on the internet, you have quines which takes 2 lines. So if you use all the special kind of quotes, because you have 3 kinds of quotes in Python, and you use some functions of Python that allows you to write special characters and then evaluate them, you can write a quine in 2 lines. If you go to Wikipedia, they have a Python quine in 2 lines. And yeah, but the point is exactly the same. You will see every time you see a quine. Actually, if you know of a quine where you don't have this kind of dichotomy of data and code where you use the data twice, I would be very interested. But as far as I know, it's kind of the only way to make quines using this data twice. So yeah, so this thing I will copy. I will debug it later. I will put it here so you can play with it. And we'll see at the end of this part, will also, okay. Yeah, okay, let me make that later because it's kind of a mess. But we'll see we can do much more with quines. Right? But let's return to the theory. So any questions about this? If you're confused, again, it's normal. The best way to get unconfused, it kind of take your favorite programming language and say, okay, I give myself 1 hour, I will try to make a quine. That's exactly what I did with this Python quine. I had written quines before, and then I started writing this one. I said, oh, I have this problem that this quote, I must do this shenanigan with the quotes. And as you do that, you kind of, something clicks at some point, you say, okay, I understand now. But just from somebody explaining it to you, it's kind of impossible to understand what's going on. And that's normal. But yeah, but let's continue anyway. So we have this quine, we have this data and code part. And this thing seems like a kind of a technicality of computer science of how to make self-reproducing program, but actually turns out that it's very similar to what happens, I mean, to the solution at least that life has found on Earth to self-reproduce. So why is that? So let's go back to the von Neumann self-replicator. And let's look at it from the point of view of these quines that we explained. So remember, it has a tape reader, and a constructor arm. And yeah, so we implemented a Turing machine. So this was a Turing machine. But since a Turing machine can make all programs that also Python can make, we can actually put this quine program on this Turing machine. So how would it work? So last time we said that you have the Turing machine that has an A part and a B part. And the A part is the data, which essentially contains a representation of B. And so for the von Neumann Turing machine, the A part is not really useful. All we need to do is take kind of the B part, so the description of the tape reader here, and put it on the tape. So if you remember the discussion about representations and output, here the input representation for the Turing machine is a binary encoding of the down arrows. So remember, the tape is just a bunch of down arrows which represent zeros and ones. So we take the description of the tape reader and put it on the tape. So the tape contains the blueprint only for this part, right? So the tape reader, yeah, is exactly not B, but rep of B. And the representation is with these arrows. And so the tape reader, what will it do? It's very simple. What the tape reader does is it reads the tape, it constructs what's described on the tape. So it will construct a tape reader, and then it copies the tape, right? Use the data twice. So yeah, and here, if you remember the discussion about the outputs, here the output of the Turing machine that we choose is just that it should physically construct whatever it wants to output. So okay, that's all good and well. And so if you look at this, it looks extremely similar to what happens at the level of a cell, right? What is a cell? So you have kind of the tape reader. So here I should not have called this code because first we separate data and code. So this is data, not code. So you have the cell. So the cell itself, excluding the DNA, is just a machine, right? It's a tape reader. If you put some DNA inside, it will kind of read the DNA and try to translate it into proteins or whatever. And then the DNA itself is just a bunch of data. And what does this data describe? It does not describe the DNA itself. It just describes the actual cell. And so when a cell needs to duplicate, it needs to use the DNA twice, right? Because first, it needs to use the DNA to duplicate kind of the machine, so the cell. But of course, that's not enough. You should also duplicate the DNA somehow, right? So the DNA contains information only to create the cell, and then the cell is able to copy the DNA as well. So even in real life, you have this kind of use the data twice if you want to self-reproduce. And that's kind of, yeah, that's why I believe that it should not be possible to have quines without that, right? So the life had to figure out how to make quines, and it did it in exactly the same way we did it in Python, essentially. So yeah, so one fun thing is that, so it's kind of convoluted, it's not as simple, but this von Neumann machine preceded somehow the discovery of DNA, not exactly actually, people had already discovered that there was some kind of code. But there is this guy, Sidney Brenner. I don't know much about him, but I know he won a Nobel laureate about DNA-related stuff. And he shared an office with Francine Crick of Watson and Crick. So these two people are the one credited from discovering the actual helicoidal structure of DNA. And usually what people say is that the idea for DNA is credited to Schrodinger's book, What is Life? Okay, in this book, he kind of talks about you need some kind of code that explains how the cell works. But this guy, Sidney Brenner, said that is actually wrong. Okay, that the thing that inspired this kind of DNA discovery was von Neumann's work on self-reproducing automata. And why is that? So the reason is that because in Schrodinger's book, he says that the chromosomes, okay, the DNA, contains the information to specify the future organism and the means to execute itself, right? To execute the chromosome. And as we have seen, that's not true. The data contains only the information about the code. It does not contain information about how to run the code in some way. That's the code that does this part. And so this one's kind of a kind of nitpick, but it's kind of important. In von Neumann's view, he understood that the tape can only contain the description of the cell. It cannot contain the description of kind of how I mean, it does not contain the information to execute the cell. This is kind of either the cellular automaton or in real life it's physics. And okay, that's kind of cool. But you can see how this, okay, we have the DNA here and the cell here can inspire very easily this thing. Okay, any questions about this? All good? Great. So now let's go on to the non-constructing proof. And this is going to get kind of technical, okay? It's okay if you cannot follow, but I'll try to make it as clear as possible. So what we've shown until now is that there are self-reproducing Turing machines. And the way we showed that is by explicit construction. So remember this A-B construction, essentially what we did in Python. So since we shown this for a Turing machine, by the Church-Turing thesis, this is true of any Turing-complete program, since every program that exists for Turing machine should exist for any other Turing-complete language. Of course, there is one caveat that we said that you should choose appropriate representation and outputs, because from some choice of outputs, you might not be able to do this. Like a simple way to see this, yeah, is exactly that. So what we said last time, the Turing machine can only act on the tape. It will never be able to create another Turing machine. It will be able to create a representation of a Turing machine on the tape, but not the actual Turing machine. All right. So now we want to show this existence of self-reproducing Turing machine, but we're going to do it more precisely and much more abstractly. So technically, it's by construction, but you will see that it's not easy to actually put it into action. But technically, it's still a constructive proof. And the reason we want to do that is that it will show us more plainly what assumptions are needed for this self-reproduction. Okay, so we start. We first assume that there is a computable function P that goes from the naturals to the naturals, such that P of n is a Turing number for the programs that output n. Okay, so remember we already defined this last time. So P is not a function. P is a function that allows you to create Turing machine that prints some specific stuff. Okay, so for example, if I can use P to create a Turing machine that outputs hello, okay, all I need to do is evaluate P of hello, and this is the Turing number for this program. Okay, so of course here P I said is from the natural to the naturals, but just to abstract a bit, we can assume it takes strings. So what P does for you is that you give him something that you want to output, and it gives you the program that outputs exactly that thing. All right?
I
Yes?
don't want to be nitpicky, but there is several programs that can output n, right?
There are several programs.
the program
Yes,
that
sorry.
outputs.
Yeah. So
A program.
A program. Yeah, you're right. Exactly. Yeah, you're right. So there are, of course, there are several programs that do the same thing. So this one just gives you one program that outputs. Yeah, thank you. So, right, in the constructive proof, we also had this print function, if you recall. And so what will we write? We will write it like this. So remember that phi underscore something x means take the Turing machine P of n, this is a Turing machine, and run it on the input x. And this is what is the output of the Turing machine, right? So what we mean here is that if you run the Turing machine P of n on any input, it will just output n. Okay, nothing too fancy for now. So yeah, by phi n of x, we mean the output of a Turing machine n given x as input. And to make things simple here, input will just be whatever is on the tape when the Turing machine starts. Output will be whatever is on the tape when the machine halts. Very, very simple. All right. So now we are looking for a quine, a Turing machine quine. So what is the defining property of a quine? Well, let's name the quine Q. Q is the Turing number for the quine. And the defining property is simply this one. So what does this sentence mean? It means take the program Q and apply it on X. Its output will be the same as the program P of Q applied on X. But the program P of Q applied on anything is Q, right? This is the program that prints Q. So what we just said here is a quine is a program that when you run it on any input, it outputs itself, right? So as I said, in English, this equation means the effect of program Q is exactly the same as the effect of program P of Q, namely to print Q, right? So it's clear why this is the definition of a quine, right? It's just a Turing machine that outputs its own Turing number, right? Or its own code, if you prefer. So now we'll introduce some notation, which is quite useful. So we'll write n equal phi m. So I would say equal in computation or equal in execution. So what does this mean? This means that those two numbers or those two Turing machines output the same thing for all inputs. Okay, so they are effectively the same Turing machine. They don't have to have the same code, right? Just as in Python, you can have thousands of ways of implementing the same function. So equal phi means that if you run these two Turing machines, they will do the same thing. They do not have to be the same Turing machine. And that's important. So so as a concrete example, say I have a Python program which I call P1. Then I write some extra comments on my Python program. This technically becomes another Python program P2 because the source code is different. But still, we have P1 is equivalent in computation to P2. All right? All good. So if we restate again this defining property of the quine, all we need to do is find a fixed point of the function P. Right? We need to find Q such that P of Q is equivalent in computation to Q. Right? So if you apply this definition, you will see that you recover this equation here. Means that the quine does the same thing as printing Q, so the quine prints itself. So the reason that's the reason why this existence of quines is sometimes called the quines fixed point theorem, because we are finding a fixed point for this function P according to this kind of strange equality, right? So here for the quine, we just need to find the fixed point for this specific function P that prints stuff. But we'll see that we can do much, much better than that. So instead of giving me the specific printing function, give me any function H that goes from the natural to the natural. And I only ask of you that this function is total. So by total, it means that it is defined on all natural numbers. And this function is computable, which means that I can actually design a Turing machine that does the same thing as this function. That's all I ask. And if you give me this function, I can find some number n, or some program, if you prefer, if you consider it a representation, such that h of n is equal in computation to n, right? So this is much more powerful. It means that any function has a quines fixed point as long as it is total and computable. So in particular, the printing function is total because you can print any number that you wish, of course. And it is computable. I mean, this is kind of a bit more involved, but it is computable because you can make a Turing machine that outputs anything that you want on the tape. So before starting on the proof is actually like 3 lines. So in principle, the proof, like understanding the equivalences is super easy. Understanding what's going on behind, it's kind of harder, and I haven't understood it completely myself. But all you need is these 2 things. So the first thing is universality. So remember, universality, what it means that there is a Turing machine U. There is a Turing machine U that, given a program and an input, does the same thing as the Turing machine acting on the input. Okay, so the Turing machine U simulates any Turing machine. And then we have the so-called SMN theorem, which kind of does the opposite. So you have a program that takes 2 input, and it tells you that there is another program that you can compute, which does the same thing, but we fix one of the inputs. So it takes only the y input and the x input is fixed. Okay, so these 2 equations are all we will need. So before starting, we define a last function, which is slightly different. So we define the program u tilde, and all we do is just apply universality twice. So the equation that u tilde satisfies is the following. So it takes as input 2 programs, n, m, and then some variable x. And what it will do is it will do this thing. Okay, so let's unpack it. In English. What does u tilde do? So, given 2 programs n and m, it first will simulate the action of n on m. Okay, we know we can do that because we can simulate any Turing machine by universality. So we're allowed to simulate n on m. Then it takes whatever this simulation had as output, and it says, okay, I will consider this to be a Turing number for another Turing machine, and I will use it to simulate this Turing machine on X. Okay, this is this equation here. So this means simulate the result of the simulation of n on m on X. Okay, that's kind of starting to become convoluted, but as you can see, this equalities here is just 2 applications of the universality theorem. Yes. So this is kind of a level 2 universality theorem. Instead of simulating just one machine, we simulate a machine on another and then simulate again this one. But there is nothing special going on. Yes?
Sorry, what does it mean? Totally computable?
Total computable, yeah. So this, I just mean that it is both total, so defined for all n and x that you can feed it, and computable, it is actually implementable by a Turing machine, this S. So it just means that you can write a program for any n and x.
Doesn't crash.
Doesn't crash, yeah. Doesn't crash, doesn't loop. Right, so when I go through this explanation of the existence of u tilde, we see that u tilde exists because you have universality, and essentially all u tilde does is simulating some Turing machines, so u tilde exists. The only condition is that the program n should be total, right? Why is that? Because the first thing that u tilde does is simulate phi n on m. And if n is not total, this computation might never finish. So u tilde might never be able to do the second step. So for even for phi n of m to be defined here as a Turing machine, you need n to be total. But that's all you need. Yes.
So can we access the Notion?
Yes, it's all on the website. Not yet, but I can give it to you. Yeah. Up. I will send it to you by WhatsApp. Here you go. Yeah, actually, maybe I should put them on the website before. It might be useful for people to follow on there. All right. So we have this function, strange function u tilde, and now that we're done, we're just going to apply these three equations one after another, and you will see that we'll construct a quine. Okay. So we start. You give me any program T. Remember, we want a fixed point. Okay. Yes. 1 second.
Sorry, I have a question about you used quines fixed point theorem. Is that right?
I didn't use it. I will prove Klein's fixed point theorem. Yes. So Klein's fixed point theorem, it means that there exists a program Q that satisfies this equation for any H, which is totally incomputable. I mean, that's what I call Klein's fixed point. There might be some different definitions, but all right. So I start. So what we want to do is find this thing, right? This is our goal. So I start by constructing some random stuff. Okay, given a program T, I consider the following number. This is a valid number, right? Because S of TT is a total computable function, so it gives me a number. H, I can apply it to anything, it will give me a number. So this is a valid number, okay? And in particular, I can rewrite it as H tilde of T, right? It's just H composed with S. I mean, this is obviously clear that we can do. And since H and S are both computable, where H tilde, it's easy to convince yourself that it's computable, right? You can just come up with the Turing machine. The Turing machine takes T, it computes S of TT, then it computes H of this, and that's H tilde. All right, so we have this H tilde function. Okay, and then we have this first line here, right? So let's see. So we have phi of this number applied on X. So we are considering this as a Turing machine and we apply it on X, right? This is equal to this by definition of H tilde. And then here we use that H tilde is computable, right? So what does it mean it's computable? So let me write it as a line. Since H tilde is computable, there is a TM H such that phi of H on X is equal to tilde H on X, right? That's all that it means. It means that I can design a Turing machine that does the same thing as H tilde. Okay, that's what I replaced here. This H tilde I replaced by phi of HT. Yeah, that's good, H tilde. And now here, I just use the equation that we have for U tilde, right? So remember, so U tilde allows to go from this thing, so phi of phi something, to phi U tilde of these two things. So this is the equation that I apply. You can see that I just blindly apply what I proved there. So this is equal to this. And this we can do why? What were the condition? The condition were that big H is total, which is the case. And the other condition was that we have a universality, but we do since we are dealing with Turing machines. So this is true. And now the last step, I use the SMN theorem to take this H. My computer is going to turn off. Huh? Well. All right. So, yeah, I think it's good. So yeah, so now we have this U tilde that takes three parameters, H, T, and X, and we'd like to get rid of the parameter H. You will see later why. So we use the SMN theorem to plug this H back down there. So we fix the H. And now this new program, S of U tilde H, just takes T and X as parameter, right? And this S of U tilde H, I just called M. So the only things I use here is that H is computable, that we have universality, and that we have the SMN theorem. So not many assumptions, but okay, universality is quite a big deal. So what did we do here? So it's not clear what we did, and I could not have found this myself, I don't think. But all this work that we did is to define this function M that does the same thing as this function H of STT. And what we wanted to do is take this t dependency here and remove it and put it here, right? Now the t dependency is kind of a free parameter. Okay. And now we have the magic that actually happens. We consider a new program, Q star, we will call it. And this program is defined as S of MM. So remember, what does S do? This program here is essentially the program that does the same thing when M is applied to M. So S of MM is more or less the same thing as M of M, right? Again, as we always do in this kind of logic proofs, etc., we have a bunch of self-reference. Here we have S of TT, so T acting on T, and now we have S of MM, M acting on M, right? So we're allowed to do this. We can act any program on any other program. There is no reason we do not. And then, okay, let's see what happens with this Q star, right? I name it Q, so this will be the actual quine. So let's apply blindly what we know. So phi Q star on X. This is phi of SMM on X. This, by the SMN theorem, is phi M acting on MX. This, by definition of M, so remember M is this thing here, is equal to phi S u tilde H MX. But by definition here, this thing here, we can jump to here. These are all equalities, right? From here to here. So this is phi H tilde M of X. And H tilde of M, remember, is H of SMM. But SMM is again Q star, right? So this is phi of HQ star X. So we have phi Q star X is equal of phi HQ star on X. And kind of magically, we have constructed our fixed point. So unfortunately, I cannot give a lot of intuition. I haven't developed too much myself here of what's actually happening. I can just give you kind of some locations where we are doing stuff. So the key here is again self-reference. So we start with a program acting on itself. This allows us to construct another program which makes the same thing. And then we take this new program and we make it act it on itself. And so this is just for the people that are familiar with lambda calculus. So there is something called the Y combinator. And if you look at the formula for this thing, we again have this picture. So you have two things acting on themselves, but twice. So this is the same thing, but hidden. But okay, this is not a lot of intuition. The important thing here is that even if more or less like me, you didn't understand why each step was done, I'm sure you can just take these three equations and start from here and follow all the steps and agree with me that each step is valid. And so that the proof is correct. So this is the proof, and now we're trying to decorticate it a little bit. But before that, let's have a little question on the Slido, which the code is here. So remember, you go on slido.com and then you can answer to the polls. So the question is, yes. So we have this function h of n, right? We said that we can find a clean fixed point for any function which is total. Obviously, this function is total and computable. It just adds 1 to n. So the question is, does this function have a clean fixed point? Right? It's kind of strange because h of n is n plus 1. So how will it have a fixed point? So I'll let you think about it and answer on the Slido.
Can you scroll up, please? For the proof?
Yep. Where do you want to?
I just want to see
the proof?
The first box. Yeah, that's it. That's good.
Why does it want? Oops, sorry. I'm going back. C'est pas très grave. So the function is h of n equal n plus 1. So what is what is the deal with this function? Okay. And then we have to make the pause already. Okay. Let's wait 1 minute more and then we'll look at the results. Okay, I think everybody has the time to think. So let's look at the results. So we have the majority of people that trust in my proof. That's good. There are some people that kind of do not. So the correct answer is that this function h does have a fixed point. So somebody was kind of overconfident on the no answer, but that's fine. That's very good. So there are a few people that said yes, and I know how. So is there somebody that wants to kind of give the idea for the answer? Yes?
So you need to choose a representation for your numbers on your tape, right?
Yes.
And which means that all natural numbers will have some valid tape representation, but not all states of the tape will be valid natural numbers. So the fixed point for h can be a tape that does not represent a natural number, even though you're thinking of your function as operating on natural numbers.
Okay, that's not the answer I would have given. So the answer that was proposed, just for the people on YouTube, was that not all natural numbers on the tape are valid representations. That's true. Okay, if you have to choose a representation and you could have some non-valid natural numbers, but you could choose a representation where every tape configuration is a valid natural number. There is a way to do that because you have a bijection between finite tapes and natural numbers, right? So this could be the answer in some cases, but it's not the definitive answer. Any other attempts? Otherwise, I will say why I think it's true. So the idea is really that this function h of n clearly does not have a fixed point in the usual sense, right? So there is no n such that h of n is equal to n, obviously by the definition. But the point is that Kleen's fixed point says h of n equal phi to n, right? So what does this mean? This means that it does not mean that h of n must be equal to n, right? It just means that there will be when you execute h of n and when you execute n, you will get the same output. So what it means is there is a program n and a program n plus 1 which do the same thing, right? That's what they mean that they have a Kleen's fixed point. This means these two programs do the same thing. They are not the same program. They have different codes, right? Because they have different Turing numbers, but they still do the same thing. And what's really interesting, I find, is that it's interesting that you have two programs. You have always necessarily two consecutive programs in your numbering that will do the same thing. So yeah, so I think that's the resolution of the thing. I might be wrong, but I think that's the way to say it.
I think you're right. And so somehow, in terms of the quines that you showed
Yes.
initially, I think you could say, that your quine actually doesn't just print itself because it does a lot of operations, which, is not the same as print this code.
Yes.
But
yeah, exactly. No, of course.
But
yeah.
I think it's kind of.
But it feels like surprising that in any way that you decide to enumerate your programs, you will have always two consecutive programs which do the same thing. It's kind of
with any gap, or with any computer.
with any gap. Yeah, with any gap. That's kind of the crazy thing. So this is the resolution. You have to be very careful. We are not looking for a fixed point. it does not give us the same program. It does programs that do the same thing. And this is very different. Yes?
Did you try like make a real, I don't know, like numbering of programs and then do like
Yes.
cause and shift?
So the program
And it
is,
seems like a huge,
yeah, so it seems that this is kind of constructable, but not so easily.
yeah.
But this would be a great project. If somebody is like kind of coming from informatics or whatever, you could say, okay, let me actually do a numbering and let me try to actually apply this proof. Because, for example, in Python, remember, we implemented S, we implemented U. So nothing stops you from defining M. But I think it's very non-trivial and likely we'll get like,
The numbers get very, very
yeah,
big.
the numbers will be impossibly big probably. So, but it's, yeah. But even attempting that would be a valid project. I mean, for the project, you really have all the freedom in the world. Pick something that you want to do, just some connection to the course, and you're good. So before doing the pause, let me finish this thing. So we start with the other part after the pause. So yeah, so let's look at the proof a bit more, even though I cannot say so much, but we can at least see what assumptions we need. So what is for sure is that the SMN, the SMN theorem is essential. Okay, we cannot really get rid of it because we are using it twice. We're using it here, and we're also using it here to actually do the proof. So the SMN theorem, we need it, but as you remember, the SMN theorem is really trivially exists in most computation paradigms. It just means that, okay, this used to be an input variables. Now I just hard code it into my code. There is nothing crazy going on here. So the other thing that we need in this proof is universality. But if we want to relax the scope of the theorem, because we never wanted fixed points for any function, right? We just want fixed point for the printing function, because that's what allows us to have self-reproduction. So at what point did we use universality, right? So we used it here. Okay, the goal of universality was kind of to take this variable t and put it as input instead of it being kind of here in the program. So that's what you use universality. But our goal is really going from here to here, right? That's what we need to make the proof. And so we can kind of bypass this whole thing because, yeah, our goal is to find this thing. So here I can explain with words what does M do. So with universality, okay, we show that this M exists for any H that we choose. But let's say that you want to do this just for a single H, a special H that you choose. M, what does M needs to do? So M needs, given T, it needs to compute S of TT. So M needs to be able to kind of emulate S. Then it also needs to be able to emulate H. And then, even more, okay, that's kind of, and then, yes, and then it needs to be able to emulate this result here as acting on X. So it needs to simulate a lot of stuff, but it does not need to simulate all Turing machines, right? It needs to simulate these Turing machines here for any T. And of course, for given H, this might be equivalent to universality because it's still a lot of Turing machines, right? Because it must simulate this for any T. So that's a lot. But it might be possible that such an M exists if you choose a specific H. Right. So this is what I mentioned. So for the procedure above, M needs to be able to simulate not only H, but all programs of the form H of STT for any T, and that is a lot. And that's why we just say, okay, let's use universality, and so that we know that we can do that. But yeah, let's take an example. Let's take H of n equal 314. This is a total function. It's computable. Just output 314 for anything. And in this case, M is very simple, right? Given T, it just discards T because it does not affect what will happen. And it simulates the Turing machine 314. So M essentially is the Turing machine 314. Right? Because H of anything is 314. So here, we don't need to compute this because we need to simulate H of something, but this is always 314. So all we need to do is simulate the result 314 acting on X. So you see that in this case, M is just 314, and you don't need universality to find a fixed point for this specific H. Okay, in fact, the fixed point is obvious, right? It's N equals 314, because that's an actual fixed point of the function, so it's also a clean fixed point. So for some H, you don't need universality. So to end this thing, so we are not interested in find clean's fixed point for any H. We are specifically interested in the case where H is a printing function, right? Because we want a fixed point of the printing function, which is just a quine. So depending on which printing function we choose, okay, we might have, for example, limited printing function, which can print up to n characters. It might be possible that you have indeed self-reproducing program for this printing function without Turing completeness, so without universality. Okay. In other words, universality is not required for self-reproduction. It's sufficient, but it's not required. And I say this is obvious because you can decide any cellular automaton. Let me give a very simple example. Two colors, black and white. When you have a white dot, it becomes two white dots. That's it. I have a self-reproducing thing. Obviously, I mean, this thing is probably not Turing complete. All it does is duplicate the white dots, but you still have self-reproduction. Okay. That's why I say it is obvious. But universality will be required for universal self-reproduction. And for this, I don't know if this term already exists somewhere, so I don't have a precise definition, but the gist of this thing is that we want to not only have self-reproducing programs. We want to have self-reproducing programs that can also carry arbitrary amounts of information. So for example, in the 314 case, or the dots case, yes, you have a self-reproducing program, which is a white dot. But we would like a self-reproducing program that is can also carry a bunch of other stuff that will also self-reproduce with it. So here I have two definitions to give you. So there is the softer definition, which would be, for any number x, there exist a program that writes x on the tape, erases it, and then self-reproduces. This is kind of more involved because you're not just printing yourself, you're doing other stuff before. So essentially this program carries the information of X, but it also self-reproduces. And this you can show for the exact same proof. You just consider clean's fixed point for the function H, which is write X, erase, then print N. If you have a fixed point of this, you will have a program that writes X, erases it, and then prints itself.
I don't understand. Why did it erase it?
It's just to show that it has the information, that it's capable. I mean, it was just a way to show that it carries this information X. Because otherwise, what does it mean for a Turing machine to carry this information?
Okay. So it's just...
It's just a kind of strange way of saying this X is defined somewhere in the Turing machine. Right?
And so it moves.
Yeah, it just shows, okay, I show you that I have this X in my memory, and then I just erase it because we said that the output is all the tape, right? So it's just a technicality. All that it means is that this program carries the information X. So it has a universal self-reproduction because not only you can have a program that self-reproduces, you can also have a program that has a bunch of stuff inside and also self-reproduces. And so here, I said it's not so clear that universality is absolutely necessary. I would say universality is not necessary. And the thing is, because you can come up with cellular automata, for example, you can come up with some rules that given an initial configuration, this configuration will be duplicated. So in that case, you have this soft universal self-reproduction because anything that you put will be replicated in some sense. Okay, then you can discuss maybe writing X and erasing it makes it so that you need universality, but okay, the idea is that you don't have just one self-reproducing program, you have a bunch. And then the strong definition is kind of more important for life, is given any total computable function T, there exist programs that takes Y as input. What it does, it computes T of Y because it's total, and then it self-reproduces. So this, in a way, is kind of what animals are, right? They're not just a program that self-reproduces. They do a bunch of stuff during their life, and then at some point they self-reproduce. So this is the kind of strong universal self-reproductions. You have a function that does some computation and then self-reproduces. And with the cleans fixed point, I'll let you read this at home, you can also show that these exist, right? And in this case, I'm like 99% sure that you need universality for this, because our u tilde must simulate the underlying function t here. And this is any total computable function. So I would be surprised if you can do this without universality. Okay, so let me finish and then we do the pause. This is really quick. I want to show you this universal self-reproduction in Python, because so far our quine just copies itself, but it's not very interesting because our only goal was to copying the code. Now I'll show you how you can put any code inside. I mean, it can carry any amount of information. So let me show you. So here, this is called an intron. Okay, and it will be some data, whatever. And what I want to do is to be able to have this thing still be a quine, and whenever I change this thing, remain a quine. Okay, that's quite interesting. So how do we do it? We use the usual trick of use the data to print the data. But the different thing about the intron with respect to the other data is that he just prints himself. His job is not to print any other part of the code, it's just to print itself. And so that will make kind of the magic property. So here I just added this code here. It's kind of annoying because I have to add a data 5, but that's fine. Okay, so here we have the intron, and then we'll have a data 5, which will contain what? Which is contain the intron, and that's the key. So here we could just copy paste this thing here, right? We could copy paste this like that, and this would work. The problem with that is as soon as I change the intron, I also have to change its definition here, which is not ideal. So here we're going to be kind of more clever and do the usual trick of putting an alias, F1. And then, of course, data 5 needs also to print itself. So we put the second alias here, right? Okay, it's kind of annoying me. And then we have to print these two, but of course, then we have to add it here. Okay, so what we did here is, as you see, we use the intron. The intron just defines itself, right? Intron is this, and then the intron prints itself here. And the result of that is that
2 new lines before intron.
2 new lines. Yeah.
No.
Yeah, here. Just one because the print adds a new line each time. So here, if I run this quine now, and we go to the copy, we see we have the intron, right? And the magic thing is that now this can be anything. So I just changed the intron. I didn't change anything else. I just rerun the quine, and it's still a quine automatically. I didn't have to change anything else. So you see, now this quine carries arbitrary information that I can put in the intron. And now you can start to do some very fun stuff, because in this intron, you could put any code that you want, right? Def, for example. Def f, print hello. Sorry, we put the aliases. Okay. And then you can start kind of executing the intron. And then, okay, here we have a new line, so I have to add it to the data 5, etc. But once you have this set up, you can paste any code in the intron and it will actually run. So this is kind of the strong universal self-reproduction. So now we have a program that does some stuff and then reproduces. And that's basically what a worm virus is, right? So the worm virus is just do some stuff here. Okay, maybe, I don't know, collect all the crypto passwords that you have on the computer and then self-reproduce to another computer. And then you can start to, if you run the first one, it will start to self-reproduce a lot, and that's it. So here we have, okay, I didn't finish it because I'm kind of late, but try think about it at home. I will also put it on the website, how you can put any piece of code here And then the magic thing is you don't have to change anything about the whole program. You just put whatever code you want in here and it will be executed. And that's the strong version of the self-reproduction. So, okay, let's make a 15 minutes break and then maybe let's make 10 minutes for this time, just to, if you agree. Yeah. So please complain on the YouTube if there is no sound, but I think there is sound this time. All right, so, okay, we won't be able to go to the end, kind of, that was my goal, but that's fine. So today, this course is kind of the first time we stop with the theory and we do actual practical stuff. Well, to be honest, there is a little theory also today, but we won't get to it today. So ideally, my first idea was to do kind of the first half of the course mostly theory and then the second half mostly practical stuff. And so I realized that kind of the theory is taking longer than I expected. So we're gonna make like 2 or 3 courses now, which will be more practical. Then we'll go back for one final theory result, and then it will just be practical stuff. So if you have some friends that left because it was too theoretical, you should notify them that they maybe should come back soon. But anyway, so today we're gonna look at the most basic cellular automaton. So we look at the von Neumann, which was kind of the first cellular automaton. Now we're gonna go on the most basic ones, which is one-dimensional and with 2 colors, 2 states. And we'll see that even with such super simple CAs, we'll get interesting behavior. So yeah, one thing on the website, on the course page, I put a bunch of stuff. So there is some information about the projects, which I will update soon. But generally for the projects, the deadline will be at the end of the course, not before. And I still have to choose, actually, yeah, I will put this poll up to kind of gauge what people would prefer. So it's just whether it would be better for you to hand in a written report, or the other thing, which I think would be nice, is to select one day or one afternoon or even 2 afternoons where people are free to come and each person does like a 5 or 10 minutes presentation showing what they did. It will be kind of hard to organize, but I'm sure we'll figure it out. So just vote on this. I will leave it up and then we'll take a look later. And for the projects, again, if you're unsure if your project qualifies, it probably does, but you can just ask me. And there will be no grades. It will just be pass or fail. So it's more relaxed for everybody. My goal is not to fail people, so don't be stressed about this. And you will get your 2 credits if you do something. Okay, so let's start. Am I recording? Yes. Okay. So the 1D cellular automaton. So the simplest cellular automaton. Okay, cellular automaton, we kind of have 2. A bit more, but a few parameters. So we have kind of the space in which they evolve, then the number of states that they have, and then the size of the neighborhood. So the simplest one is where you reduce everything as much as possible. So we'll be in 1 dimension. So the full state of the system is just a line. And we'll have 2 states. You might say, okay, why don't you consider the 1 state CA? Of course, the 1 state CA is just the thing that remains the same color forever. So you could say this is the simplest, but it's certainly not an interesting one. So the world is Z, okay? In principle, the world is infinite. In practice, it will not be. And each state can take 2 values, 0, 1. The neighbor we consider is the smallest possible, so it will be the nearest neighbors. So, wait, I had a picture here. Where did it go? 1 second. No, it's here. Yep, this one. Sorry about that. Yeah. So this is kind of the full world. And the neighborhood will be considered is nearest neighbor. So we consider a cell and its 2 neighbors. And this will affect the state of the cell at the next time step. Okay? Again, you might ask, okay, but the simplest neighborhood is just 1 cell. Yes, but then all the cell remains the same. I mean, the cellular automaton is completely decoupled into one cell bits, so it's not so interesting. And you could also say, okay, what about a neighborhood of 2 cells? But it's not very nice because it's not left-right symmetric. So we consider 3 cells as the minimum. All right, so again, this we already said, but let me repeat. So a rule or the transition function or the physics is then simply a function of all the possible neighborhoods. So these 8 neighborhoods here into 0 or 1. So in other words, to determine the transition function or the rule, you list all the possible neighborhoods, which are listed here, and you choose an outcome for each of the possible neighborhoods. So either black or white. So for example, for this specific rule, when you have 3 black cells, the middle cell becomes white. Okay. So there are 8 different neighborhoods, right? We have 2 choices for each cell. So when we choose a rule, we have 2 choices for each neighborhood. So in total, we have 2 to the 8 possible rules. So we have 256 different rules for this simplest cellular automata, which is not a lot. All right, yeah. So the nice thing about 1D CAs, as opposed to 2D CAs or even 3D CAs, is that we can visualize the full space-time diagram. So we don't only see what's happening now, we also see what's happened before. So this is what it looks like. Right. So what's happening here? So here, one line of this graph is the state of the CA, and then going down is increasing time. So at time t equals 0, we just had one white dot. Then at time t equals 2, we start expanding, and then, okay, we start to see those kind of triangles. So you see, for example, this triangle here would be very hard to notice if you had only seen the dynamics on a line, right? You would see some black thing that goes like this. But here in the space-time diagram, we can see these triangles. Okay, that's one advantage of 1D CAs, which kind of see the full history at once, and so they are a bit easier to analyze. And so, as we said, there are only 253 rules for 1D CAs, so it's actually reasonable to study all of them one by one. So look at the first rule, look at the second rule, and so on and so forth. And in fact, there are much less. Let me put this in quotes, unique rules, because we have these kinds of obvious symmetries. So for example, if you send all the white squares to black squares, okay, technically it's a different rule, but if you have seen one of the 2 rules, you know what will happen in the other one. So this kind of an obvious symmetry for us, if we know what happens in the black-white, we don't need to know what happens in the white-black. So we don't need to consider those. And as well as for the left-right inversion, so we just flip the image. This gives you a new rule, right? Because, I mean, for example, this image here, you see you have kind of these streaks going to the left, but there is, of course, another rule in which these streaks are going to the right. But again, this we don't really consider a different rule. And the reason we do not is because once we have one of the 2, we know intuitively what the other will do. So if we identify these rules that are connected through these symmetries, we are left with 88 rules, 88 unique rules, if you want. So that's really not a lot. And so here I just want to do a remark, because at first it seemed obvious to me, and then I was kind of puzzled. What is the reason why we consider this as a symmetry and not something else? Right? You could also consider some other type of symmetry. For example, take all the rules and kind of shift them toward the right. That's also kind of a possible way to connect 2 rules. And so for me, the reason is that these symmetries are accepted symmetries, and we are happy to identify these rules, is because once we see the dynamics of a rule, we know all the dynamics of all the symmetric things. So if it's going to the right, we know that when we apply the left-right, it will go to the left. So that's why it's an accepted symmetry. But then you could kind of try to think about it and think, okay, maybe we can define some more general kind of transformations, which whenever I know the dynamics of the CA and I apply this transformation, I can easily deduce the dynamics of the transform CA. So if this is something that interests you, you can look at some exploration in this direction in this paper, Computation Hierarchy for Elementary Cellular Automata, by Barbara, which was here earlier. here earlier, and that will join us as a postdoc. And so in this paper, they indeed look at some more complicated kind of operations that you can do on the set of rules. And and then you have you can identify more rules which are essentially the same, but secretly the same. So this is if you're interested. This is very mathematical, so it's only if you're more math oriented. All right, so now some practical stuff. So Wolfram codes. So when I want to talk about a rule for a 1DCA, it's very inconvenient to actually have to write this full thing. So Wolfram codes are just a way to compactify this kind of notation into a quick naming scheme. And the way it works is very easy. So we have 256 rules. Okay, so we'll give them a number from 0 to 255. And we want to be able to easily decode the rule given the number. Okay, and the algorithm to do that is the following. So we take our number and we write it in base 2 using 8 digits. Okay, for example, 137 in base 10 is this thing in base 2. Okay. Then what we know is that, so we have 8 different neighborhoods, right? So what we say is that each of these numbers corresponds to one neighborhood. Okay? And the way the correspondence is done, this is completely arbitrary, is just that I don't know why I wrote this. Yeah. So yeah, exactly. So the neighborhood here, this one here, we're represented by this number 001. And these numbers will go, this is in binary, by the way. So let me be more clear. So this is equal to, whoops, 001 in base 2 is equal to 1. Then this is 101 in base 2 is equal to 1 plus 4, 5, if I'm not mistaken. Okay, so this is neighborhood number 1, this is neighborhood number 5. So we just order them by their value. So the 000 goes before the 001, etc. And so this number here, 1 and 5, is the digit which corresponds to this neighborhood. So I will show you an image because I'm not explaining it very well. So the way to decode the rule is you look at this number here, and you look to the digits. So for example, let's look at the digit number 0 here. This will refer to the neighborhood which is completely empty, so this one. And the actual value of the digit 1 will tell us that given the neighborhood with 000, the cell will become on. It will become 1. Okay, so this is illustrated more simply here. So we have 137. We write it in base 2. Okay, and then each of these digits. So this is the number. This is the number in base 2. Each of the digits corresponds to a neighborhood, right? So you see these neighbors are ordered. This is neighborhood 0, neighborhood 1, 2, 3, 4, 5, 6, 7, 8. And then this 1, the fact that the 8th digit is 1, it means that this neighborhood will yield a white successor. This being 0, this means that this neighborhood will yield no successor, and so on and so forth. Okay, so you see that just give me a number between 0 and 255. Using this trick, I can decode it into the actual rule, which is this thing here. Okay, any questions about this? So the only thing that it's kind of, we need to choose arbitrarily is how do we order neighborhoods, and we just order them in this way, and then we assign them number in this order, right? So what's cool about this Wolfram code notation is that it extends to cellular automata also with arbitrary number of states and also with bigger neighborhoods. Okay, so right now we had a neighborhood of radius 1, which means that we have one cell on each side. Neighborhood of radius 2, which means that we have 2 cells on each side, and so on. Okay, so if you go through the math, if you have k states and r neighborhoods, and a radius of r, you will get k to the 2r plus 1 neighborhoods. Okay, this is because one neighborhood contains 2r plus 1 cells. Okay, because it's r cells on each side plus 1 the middle one, each cell takes k possible values. So k to the 2r plus 2r plus 1 neighborhoods. Okay, good. And if we want to choose a rule, we need to say what is the result of this neighborhood. And for each of these neighborhood, we can have k different results. So we have k to the 2r plus 1, k to the number of neighborhoods, different rules. Okay, this number grows like insane. As I first tried to implement it in code, I said, okay, it will be fine. Put k equal 2, r equal 3. Okay, I don't know, it was like 10 to the 115, something like that. So yeah, it grows extremely, extremely fast. And then you can also design a Wolfram code for this, which is much of the same. So the numbers that define each neighborhood will go from 0 to the number of neighborhoods, as before. And then to decode them, we'll take this number, write it in base k. This is just write it in base k. And then each digit of this base k number corresponds to one of the possible neighborhoods. And the value of this digit is the outcome of this neighborhood. That's just if you want to implement it. But yeah, so these grow a bit too fast. So the example I gave you, yeah, it's k equal 3, r equal 2. You have 10 to the 115 rule. So yeah, this is more than anything that you can have in the universe. I mean, I don't remember how many atoms or how many protons are in the universe. I'm pretty sure it's less than that. So that's way too many rules. So what people do when they consider like more states or bigger radii, what they do is consider totalistic or outer totalistic CAs. So what does this mean? This means that, so before, the new states depended on the precise neighborhoods that we have, okay? So each neighborhood is assigned a value. But you could say, okay, what's important is not really the actual neighborhood that you have predecessing you. What's important is how many on cells you have in your predecessor. So the totalistic, instead of assigning a possible value to every neighborhood, it assigns a possible value on the sum of the cells in the neighborhood. So for example, in 2D, if we had a totalistic automaton, instead of looking at the precise neighborhood, we say this is the neighborhood where you have 3 black. This is the neighborhood where you have 2 black. And as you see, the 5 is also 2 blacks. So these two neighborhoods are indistinguishable. They have to give the same value. Then you have the neighborhood with 1 black. Again, this one, another with 2 blacks, and so on and so forth. So then you have much less choice, right? Instead of assigning a value to each of the different neighborhoods, you assign a value to all the possible different sums of the neighborhood. Okay, and this reduces the number to manageable amounts, such that it does not grow so fast. And so this is totalistic, where you consider the sum of the values of the states, of the states in the neighborhood of the neighbors. And outer totalistic is almost the same, but the idea is that you sum the value of the neighbors, but then it can depend on the value of the middle cell. Okay, so in other words, so example, yeah, the 5 and the 6 here, both neighborhoods. Sorry, no, this is not a good example. Which one is a good example? Yeah, this one. No, it's not. Yeah, sorry. 6 and 4, okay? 6 and 4. So in outer totalistic, you make the sum only of the strict neighbors, not yourself. So for 6 is equal to 1, and for 4 is equal to 1 as well. And then, depending on the value of the middle cell, you can do different things. So you have slightly more freedom. Okay, this is something, the reason I mentioned this is because, for example, the game of life is an example of an outer totalistic CA, because in the game of life, you take the sum of the neighbors, and then you do something different depending if you're alive in the middle or not, right? So this is outer totalistic, you do the sum of the outer neighbors. All right, So here I had a question, but let me skip it. It's just some combinatorics. So the question is, how many totalistic cellular automaton? Yeah, I have the answer here. Yeah, sorry. How many totalistic cellular automata we have? And this is just to show that it grows much slower. So it goes to k to the number of neighbors times k. It's still exponential, but it's not doubly exponential. So it's kind of manageable. Right, so here I have a project idea. It's not very exciting, but I just thought about it. So the question is, remember I told you that you have these simple symmetries, kind of switching the colors or doing the left-right symmetry. So the question is there kind of a closed form formula that tells you how many unique CAs do you have, 1D CAs, in the case of arbitrary K and R under these symmetries? Okay. So this, if you're interested in kind of combinatorics, maybe that's interesting to you, but the answer will not be very interesting. I mean, we'll have an answer, it will be nice, but I don't know if it's very useful. But if you're interested by this stuff. So here, yeah, so now let's look at some examples. So we have kind of the basics of how things work. So here I'm looking at R equal 1, K equal 2. So these are the so-called elementary cellular automata, so the most basic ones, right? Just two colors and the smallest neighbors. So this is the number of the rule, the Wolfram code. And this is the output of the rule. First, when we started with a single white pixel, and then when we started with just a random initialization. So this is for a single white pixel, we get this nice fractal. Then for the random initialization, we get this kind of noise. And okay, we have our rules which are very simple. This one just translates the white dot. And again, we put more white dot, it translates. You have these rules here, which looks very simple when you have just one white dot, but then when you start putting random initial condition, it makes some more interesting stuff. And we have this one that from a white dot, it becomes completely random. And then very similar for the random initial. Anyway, you have a bunch of behaviors. Okay, this one is kind of beautiful. Yeah, I hope nobody's epileptic, right? I mean, this is kind of yeah. So this is one of another one. So this one also. Okay, you see these streaks of triangles. It's kind of cool. You have a lot of these surface triangles. Like this is very interesting. And yeah, that's a bunch of behaviors just for these very simple rules. And so, right. So the key thing here, and that's something that Wolfram likes to say, actually I can show you. I don't know if I have it here. I don't actually, but he has a book which is like 1,500 pages long. It's called A New Kind of Science, and where he studies these cellular automata. Right, so when we look at these, we see a huge range of behaviors emerging. And we also see that this behavior may be very different according to initial conditions, right? Sometimes it's very simple when we start with kind of a single dot, and then it becomes complicated once you start with random initial conditions. And the idea is that here we would like to find the interesting rules, right? What rules actually produce interesting stuff? What rules have a chance of having life develop inside? And so here I want to do this poll here just to see. So the poll is, in your opinion, just, I mean, there is no trick here. Just, I will show you three. Let me. Yes. So you have these three dynamics. Let me show them to you. Maybe I can put them side to side. Let's see if this works. Kind of. Right. So yeah, not really. Anyway, we have these three dynamics. Yeah, this is a mess. Okay, you kind of see all of them here. So looking at these three dynamics, the question is, which one feels more interesting to you? Just kind of a gut feeling. So let me zoom in into each of those. So the first one is this one. The second one is this one. And the third one. So the question is interesting, not beautiful, because some people kind of, okay, maybe for you they are the same. That's okay, but That's the question. So you have these three dynamics. Just which one do you think is more interesting? And I didn't choose the best examples for this, but well, let's see. Okay. All right, so let's see what people are answering. Okay, that's what I expected. So most people, of course, it depends on the. I'm not saying you are wrong if you answer B or C, but what I'm saying is that in general, what's crazy is we kind of naturally agree. And here I chose some like fringe examples. If I chose some more clear examples, I think everybody would have agreed. But so question of what is more interesting, we kind of have an intuitive intuition. And so for me, the way I think about it is, so for me, the most beautiful is this one. But the reason I think the most interesting for me and for most people is this one is because here you kind of see some stuff happening, right? You have these kind of streaks of triangles that collide. And then it's not exactly predictable what will happen, but you kind of have a sense that you have these things colliding together and something will happen. It's not totally predictable, but not totally unpredictable. This one here, okay, this one here, it's kind of white noise. I cannot really understand what is going on here. You have a bunch of triangles, but I couldn't say if you have more triangles here or not. And then this one looks really cool, but if you look at it, it's very repetitive, right? So you have these channels, and these channels just keep repeating. So in a sense, if I tell you, okay, do you want to see where this goes next? You say, okay, I don't need to see where this goes next, right? I already know. So we have kind of this intuition of what are interesting dynamics. And the cool thing is that among these three cellular automata, people were able to prove, Matthew Cook was able to prove that this one is actually Turing complete. Okay, so kind of this intuition that we have is pretty good at detecting the actual interesting rules, the rules that can do interesting stuff. So what Wolfram does in this book and in the papers is essentially that. Okay, he wants to try and define a classification that captures this intuition. And so this classification was initially designed for this one-dimensional cellular automata, but okay, with some caveats. In principle, at least the idea is that it's applicable to any alive system. And the classification is the following. So you have 4 classes. So class 1 is very simple behavior, where almost all initial conditions lead to the same uniform state. So no matter what you initialize, you go to the same state. I didn't have any example of these in the pictures, but we can see afterwards. Class 2 is, we have different possible final states, unlike class 1, so it's kind of a bit more complex. But all of them consist of simple structures which remain static or periodic. So in particular, this thing would be class 2, right? So you have a lot of possible things that happen, but then these things are very periodic, very fast, right? Class 3 is, you have some complex behavior which looks random or chaotic. You can have some structures appearing, but it's kind of hard to predict where they appear. So this is typically this one. And finally, class 4 is none of the above. So you have an equilibrium between class 3 and class 2. You have some randomness, but you have also some long-lived structures, and you have some non-trivial interaction between the structures. So when you read this, you say, okay, that's great. I haven't learned anything more than what is interesting is class 4 is when it looks cool. Class 3 is when it looks random. Class 2 and 1 is when it looks periodic. And that's essentially what it is. Right? It's not more rigorous than that. And also you have problems. Okay, what about initial conditions? Some things are class 2 for some initial conditions, but class 3 otherwise. And let me leave you with that. So Wolfram's conjecture is that class 4 CAs, even though it's not well defined, can do universal computations. Okay. So in other words, if a CA dynamic look intuitively interesting, they are also Turing complete. And you have very few examples of this because it's generally very hard to prove Turing completeness. At least people haven't found a way to prove it other than actually constructing a Turing machine. And yeah, so Wolfram's thesis kind of is class 4 CAs can do universal computation. So in other words, things looks complex and not random means you have some Turing machines in there. Right. Okay, let me finish here. Yes, 2 minutes. If you need to go, you can go, of course. Right. So we have one side of the equation in that being Turing complete does imply the existence of unbounded complexity, right? Because you can do everything a Turing machine does. So in particular, you could set up a Turing machine in your cellular automaton, which simulates the standard model of particle physics. And so you can simulate our world inside. So it is at least as complex as our world. Yeah, given appropriate representation and output, whatever. And so here I have kind of a food for thought question. So if we were able to define some kind of precise notion of complexity, kind of like these classes, but something which is precise, could it be that we have kind of an equivalence between complexity and Turing completeness? In other words, you have a score for complexity, and if your complexity is above 6, well, okay, this means that you're just Turing complete, okay? Because if you can do things complex as level 6, there is no other way to do it other than having Turing machines. Okay, that's one. So this is an interesting question because that kind of the questions I'm doing in my research. So our goal is to kind of design some sort of notion of complexity which can kind of be linked to that. And yeah, and the way we do it is really connected to the human intuition. So trying to determine when things are not too random, but not too predictable either. Yes?
Would it also be linked to like how fast dynamics is? Because for some of the things it seems random, but it could still be Turing complete.
Yes. So the question is, could it be linked to how fast the dynamics are? And yes, of course. So for example, it might be that for this kind of super noisy automata, if you zoom out a lot and wait a long time, then you start seeing some mega structures, and that's definitely true. Also, it might be that when you have a chaotic cellular automaton, even if it's really like looks super random, there is a way to interpret this randomness which actually does computation for you. This is really not impossible, but these are some completely open questions. Yeah, because yeah, what it means for a cellular automaton to be Turing complete is also not so clearly defined, right? Because you need to choose a representation. So what will be the representation of the Turing machine? What does it mean to have an output of the cellular automaton? And all these things are not defined precisely. So you might be scared that if you choose a perfect output, you can make Turing complete any automaton because kind of the computation is done in the definition of the output. So this is a completely open question. It's not really defined well. What does it mean to be Turing complete for a CA? Usually it's kind of intuitive. People say, okay, look, I constructed a Turing machine. This is the tape. You have to interpret it as a tape. This is the output. You have to interpret it as the output. And people say, okay, this is reasonable. It's Turing complete. But it's not precise. So on the elementary cellular automaton, which are class 4, so the interesting class, as far as I know, there are 2 which are believed to be class 4 or classified in class 4, is this one here, rule 110, which was proven to be Turing complete, well, proven with these caveats, and rule 54. And the reason, okay, it's believed to be Turing complete, it's not proven, is because you have, again, all these kind of gliders, these streaks, that you can think that probably if you collide some streaks, you can use them to make some logic gates, essentially. And okay, I will leave you with that. And the next time, I wanted to do this today, but no time. Next time we actually look at some code, I will show you. I will also put it on my website if you want to look at it before. But it's basically some code that allows you to implement some cellular automaton with the least amount of boilerplate. All you have to do is define a rule, define a way to show your automaton, and then it just runs. So that's it. You're free.